Welcome to Chemistry Explained. Today we start the second facet of the general chemistry course, the introductory facet ended with oxidation reduction equations. Most of this facet is going to be theoretical. Chemists discovered quite early that there was a lot of things that they actually could not view with the naked eye, and thus the theories that occurred. What we're going to do in this section is explore these theories. Now, I'm not going to go in great depth. I will have some problems that I will use for illustrations that you can see. I've kind of started out with a board full of that which looks like fairly difficult mathematics, but isn't really. Let's give it a go. We start with gas laws. Now, one of the bases of gases is that they expand and contract based on temperature variations. Next time you empty a milk carton, a gallon jug, rinse it out really good, and turn on the hot water on your tap as hot as you possibly can turn it, and fill up your milk jug to the top with the hot water, then pour it out and fill it up one more time completely, and empty it out quickly, put the lid on it, and just stick it in the refrigerator. Come back 15-20 minutes later, and you will notice the gas laws in action. The quantity of gas will be constant. The changes will be related to pressure and temperature. So that's just one thing. The major impetus of the early measurement of pressure of gas was by an Italian named Torricelli. And he used mercury liquid column as his basis, because first it would move because it was still liquid, but its 13.2 or 6 density was so high that it was not easily moved, and it gave him a constant pressure is equal to force divided by the area pressed on. Also in this time was 273 Kelvin for your basis for temperature, and that's equal to 0 degrees centigrade. So we'll cover that later on. All right, the first of the champions of gas laws is Boyle, Englishman. He says that pressure times volume at a constant temperature is equal to a constant. Thus, he formulated that this was pressure times volume 1, both first, is equal to pressure 2 times volume 2. Now, this, on the surface of it, looks like a duh comment, but it's actually quite versatile. If you know 3 of those, you can solve for the other one. This is like algebra junior high almost, that if you know pressure 1, pressure 2, and volume 2, you can solve for volume 1. And it's straightforward and easy problem to do. So if you're terrified of mathematics, that should unterrify you, because you can all divide. The next illustration is the pressure volume graph that's illustrated on the left-hand side of the board there. Notice that as the pressure increases, the volume decreases proportionally. And that pressure is indicated in mercury. Hg is mercury. The next purveyor of law was Charles. Charles's law basically says with constant pressure, gases change volumetrically based strictly on temperature. Now, in the graph, you start at 300 degrees below zero centigrade, so it's pretty chilly. And zero here and 100, 200, and 300 degrees. And what you see is a straight line function of hydrogen gas, water, methane, and helium, showing that the line function is fairly constant and predictable. You can actually formulate a problem. You say that a gas at 15 degrees centigrade at 2.58 liters, what's its volume at 38 degrees with the pressure constant? Well, you can do that pretty straightforwardly. The volume 2 is the unknown. The temperatures, temperature 2, which is the final one, would be 38. Temperature 1 would be 15 degrees, 2.58 liters. Just punch the numbers in on your calculator, and you'll find the new volume. None of this is rocket science, and nothing here that I'm going to cover is complicated mathematics. I purposely avoid complicated mathematics in general chemistry, especially first semester, because there's no need in it. Yes, I can provide you a fairly difficult calculus-based illustration in some of these concepts, but it seems like needless intimidation. My effort here is not to intimidate you in any way. It is to explain things to you, and hopefully you'll get some understanding. Next on the list is the fabled Avogadro. Avogadro's number we've already talked about, which says that in any given volume of a gas, if the volume is constant, the pressure and temperature are constant, the gases all contain the same number of particles, which is 6.02 times 10 to the 23rd particles. So a liter of hydrogen in a liter of helium and a liter of methane gas all contain 6.02 times 10 to the 23rd. Now the hydrogen and the helium are elemental, the hydrogen being a diatomic molecule and helium being a monatomic, and the methane is a molecule. So the difference is what you have for the type of particle involved. Now you can actually do some of these Avogadro problems. What we have here illustrated on the right side is oxygen gas being changed to ozone. You do this electrically. And of course, when you look at it, you see immediately, because I've been trying to drill into your head, that you got to have the same number of atoms on either side of a balanced equation. So you'd have to go get something to balance it. You'd put a 3, good old steady nerves, 3, and then put a 2. Now you got 6 atoms of oxygen on the left side and 6 atoms of ozone on the left side. Now the problem says you got 12.3 liters of 0.5 molar oxygen. You want to change it to ozone. That's the equation. And again, you got volume and concentration. You would merely change the 0.5 moles of oxygen. Again, you got 2 to 3, 3 to 2 if you wish, mole-to-mole ratio on either side of the reaction. So 0.5 moles times 2 divided by 3 gives you 0.33 moles of ozone. This is, again, not complicated mathematics. It's what I call fill in and grind. You punch them into the calculator correctly, you get the answer correctly every time. Now, this is a lot of stuff, and I went through it fairly briskly. I hope I didn't lose you along on the run. Now, you can go back through this. Good thing about, well, depends on your degree of nightmare. You could always stop it and back it up and play it over again if you can stand the view of my face along with it. So that's the first section of this chapter.